Okay, so last talk of the conference is given by Alberto de la Torre, and it's also about, he's from Northeastern University, and he's talking about Kitaev materials as well. Yeah. Please take it away.
Let me start by thanking the organizers. I'm sorry I missed the first 2 days of the conference. It seemed like it was really great. But I'm happy to be here today, and I'm happy to share a work that started in the group of Kemp, actually, in collaboration with Facil too, that I've continued now at my group in Northeastern. And let me start by acknowledging all of my collaborators that participated in this work, and also thank you, Facil, because I removed 2 or 3 slides out of my talk just because of your introduction. But this talk fits within what my group tries to do, and is to try to use ultra-fast laser pulses to control quantum materials. And we want to control functional quantum materials. We want to control materials that might be useful, for new technology. And although maybe I don't need to show this next slide, I paid a lot of money for it. So let me show it. I know I need to show it in this conference, but what do I understand for quantum materials? Well, quantum materials are materials that show emerging properties over a wide range of energy scales and length scales. And these are properties that depend on the interaction of the delocalization, electron-electron correlations, spin interactions, lattice vibrations. And within these emerging phenomena, we've all studied or are studying from unconventional superconductivity to quantum magnetism, multipolar orders. And what we want to do is we want to use light to control this phase diagram, to bring a material that is in a thermal ground state and maybe create a new metastable ground state, or to bring it to another thermally accessible, but not stable in normal conditions. And how do we do this? Well, we either use a resonant excitation, so we transfer energy to the electronic degrees of freedom that then they get distributed throughout the system, or we avoid excitations. We go within the gap of the excitations and we modify the electromagnetic environment. So if you go resonantly, you can either explore the nonlinearities, you can draw optical switches, you can drive transitions out of equilibrium. If you go out of resonance and you consider the Floquet picture, what you're doing is you're renormalizing the Hopin interactions. You're adding a new periodicity, which is the periodicity of the electric field within your Gaussian environment, and you can renormalize your band structure and hopefully renormalize the exchange and control the magnetization. So within this talk, what I'm going to try to do is I'm going to motivate a system that is very close to a Kitaev quantum spin liquid system, hydrogen, lithium, iridium oxide. And I'm going to try to motivate that maybe we should all stop trying so hard doing the same thing. Sorry, Facil. Was like try to modify and achieve this limit by doing chemical substitution. And maybe we should think of a different approach based on ultra-fast light matter excitations. And maybe this is the way that we can achieve a quantum spin liquid, although transiently. Okay?
We should do both.
We can do both. Yes, we definitely should do both. Okay. I don't think after all the talks that we had this morning, I don't need to spend too much time motivating what the Kitaev quantum spin liquid is. But what we are looking is for ground states that are highly frustrated, they're highly correlated. They have a magnetic moment that is fluctuating down to low temperature. There is no long-range magnetic ground state, but they are long-range entangled. And the traditional example is to use a triangular lattice with antiferromagnetic spins. One of those spins will be frustrated. It doesn't know how to order. And your signature of frustration is Curie-Weiss behavior in the inverse susceptibility that eventually never order, and it might have an upturn usually for disorder or non-contributions that are not intrinsic to the material. Now that's geometrical frustration. The other option is that you could have frustration due to spin interactions. So for example, if you have Ising-like spins, Ising-like interactions in a hexagonal lattice, a honeycomb lattice, which is the model for the Kitaev quantum spin liquid. Now in here, I had a bunch of slides that I didn't need to use now, but the materialization was proposed in edge sharing octahedra, where the transition metal has strong spin-orbit coupling. In that case, you can show is that your Heisenberg exchange goes to 0, and the only dominant contribution will be, theoretically, your Kitaev-like exchange. As Faisal pointed out, this doesn't happen in reality. All the materials that you grow have other contributions, and you have a very large phase space depending on your ratio of Heisenberg exchange, Kitaev exchange, and any other off-diagonal interactions. Faisal has done a lot of work trying to do very fancy and interesting chemical replacement, where you try to suppress those additional terms by either introducing hydrogen or silver, among other things. Now, this has its own complexities. You are modifying the iridium oxide hybridization. What happens, what Ari asked about silver, that's literally what happens in that case. Or you can be modifying the iridium oxide octahedra and changing the local environment. Nonetheless, let me talk a little bit about hydrogen lithium iridium oxide. In this compound, thermodynamical probes show that there is no long-range order and no glassy physics. However, can we demonstrate that this is actually a Kitaev quantum spin liquid, or how close is that to that limit? But we don't have a long-range order, so what do? We try to move them to prove the magnetic excitations. Try access to the magnetic Hamiltonian. And these samples are very small. They have iridium. They are not amenable to neutron scattering. So your next best thing is actually RIXS. RIXS is a resonant and atomic sensitive probe. So you go with an X-ray that excites an electron from your cold levels into your empty states, and you look at the scatter electron that has transfer energy into the system. And that energy transfer, that energy difference, what you measure, tells you about both the structural magnetic excitations and electronic excitations in the system. And you can do this with momentum resolution. You can control the angle of incidence and the angle of scattering. In an experiment, it looks very different depending on what transition method you're looking at. In here, this is we were just last week at the SRF in France. This is a soft X-ray experiment. That's a 10-meter diffractometer. That's sped up, by the way. It moves very slowly. But you can change your scattering angle from 150 degrees down to 90 degrees. At the hard X-rays, which is what you will do if you want to measure the iridium L3H, things look much smaller. This is a 2-meter spectrometer. That's all you need to achieve your separation of X-rays coming to achieve that energy resolution in the scatter X-ray. So in here, just to provide a little bit of context, your X-ray comes this way, your sample is sitting in here, hard to see, and then scatters this way. There is a photon analyzer, which is a quartz, I think in this case it was actually a silicon crystal, that Bragg scatters the electrons with different dispersion depending on their incoming wavelength, and you detect any here in the CCD. So you measure this as a function of incident energy at a fixed angle. To start with, let's forget about the momentum. And what you end up getting is an intensity plot that depends on your incidence energy and how much energy you've transferred. This is what we call energy loss. You can see an increase of intensity as you approach and go through the iridium L3H. These are electronic excitations. This is actually for hydrogen lithium iridium oxide. You have intraatomic excitations between T2G and EG electrons, and around here you have intra-T2G excitations. But if we are looking for magnetic exchange, we should actually be zooming in near your zero energy loss, near your elastic scattering. And when we did this, and this is a quick summary of what we see, we saw some intensity that is broader than your resolution. The dashed line in here represents the resolution of the spectrometer, which was set to 15 MeV for this experiment. We pushed really, if I remember correctly, too many experiments recently. So, but we pushed really hard. And Peter mentioned about how neutron scattering experiments might be underwhelming in these systems. I make the joke that this reminds me of The Little Prince, when he was trying to convince people that that was not a hat, that was actually a snake that is eating an elephant. So what I'm going to try to convince you now is that there are physics in that broad excitation, and that those physics actually represent magnetic spectra and excitations associated to Kitaev physics. So what we did is we looked at that broad excitation across different momentum exchanges, so different points in the magnetic Brillouin zone. And what you can see is that there is not much difference at different high symmetry points. So we can go from gamma to the corner zones, to the edge zones and the corner zones, and you see the same elephant everywhere, right? You see a broad peak centered around 25 MeV with a tail that extends up to 150 MeV. And we fit that to the damp harmonic oscillators, what you might expect in the case of a system with damp excitations. It's resonant. If we move away from our iridium edge, you see that the intensity of these peaks decreases. We can also, I don't know why this still has the archive. I should have changed that. This is published in Nature Communications. We can look at the temperature dependence. And it's hard to see in here, but if you track the center position of that excitation as a function of temperature, you see, and those are the black markers, you see a softening. And this softening occurs when at the same temperature that you have a hump on the magnetic susceptibility, and that's the temperature what you expect to have the onset of spin-spin correlations. So we concluded that although you have broad excitations, these are different than the paramagnet at room temperature. So this is really reflecting the exchange Hamiltonian or the spin Hamiltonian that you have in this material. Now, there's no long-range order. We were comparing this to a Kitaev quantum spin liquid limit, and there are calculations. However, when you look at the dynamical spin factor for a Kitaev, in either the ferromagnetic or antiferromagnetic limit, you expect to see a dependence of that spectral weight as you go across the Brillouin zone. And we don't see much. There is no much difference at all these high symmetry points that you will either expect to see if you have a pure Kitaev quantum spin liquid that is antiferromagnet or paramagnet. With an antiferromagnetic Kitaev exchange or ferromagnetic Kitaev exchange. Now, we can agree that we have a proximity to that limit. And we say proximity, and I will explain why we cannot claim that this is a pure Kitaev quantum spin liquid limit, that it has an exchange of around 25 MeV and probably less than a contribution from Heisenberg exchange, another off-diagonal terms of 5 millielectronvolts. And the reason why this is not a pure Kitaev quantum spin liquid is because this is not really, even thermodynamically, it's not a simple, a pure Kitaev. There are excitations at low temperature, and there is a divergence of C over T that you don't expect for a Kitaev system. And also there are non-vanishing contributions to the NMR. So there is some other excitations in here. And you also need to realize that when you're doing this chemical substitution, when you're doing these replacements, you are introducing the intrinsic disorder to the material, both along the C-axis, so there's stacking faults, but potentially also local contributions to the iridium oxide octahedra. And there are models for this change, the effect of disorder for a Kitaev limit. And as you start to increase your disorder, still within the Kitaev limit, not going towards a zigzag or spiral order, you expect a very broad and non-dependent, momentum-dependent contribution of your magnetic excitations. So this is what we claim. And we believe that we have a spin excitation center around 25 MeV with a tail going up to 150 MeV, which is what you would expect for Kitaev-related magnetic excitations. However, we are away from the limit because of disorder. We don't see any expected change of spectral weight in momentum as we will have in that pure limit. So we call it a proximal to a one disorder Kitaev quantum spin liquid. And now is where I say, okay, well, maybe we should try a different approach. And this is an approach that is being motivated by recent work, theory work, that you say that if you consider your extended Kitaev Hamiltonian, where you consider both the Heisenberg and other off-diagonal terms, and you consider this effect of pumping with circular polarization in the Floquet regime, so you're avoiding any absorptions. You could modify the relative contribution of each of the different terms in the Hamiltonian. So for certain frequencies of pump and certain fluence, so how much energy, how much electric field you're putting in the system, you can fully achieve a Hamiltonian that is dominated by the Kitaev exchange interaction. And not only that, you can also change the relative rate between all of them. So you could potentially explore this phase diagram and control your system to different complex phases. Why is this the case? It's because you're making your electron effectively spend more time in the ligand. You're controlling this super exchange interaction. That circular polarized environment that you're created, that Floquet interaction, it's renormalizing your hopping such as you spend more time in the ligand throughout that exchange process. And as I said, you could find a regime where you might start in the very close to the QSL limit and bring it there, or actually take it away and modify the exchange interactions that you have in the material. And this is for calculations from Martin Klassen from UPenn, showing which regime you could use for hydrogen lithium iridate. If you pump in here, you might be able to increase and dominate K and suppress any other exchange interaction. So, but what are the spectroscopic signatures of this transition? So a couple of months ago, we went to XFEL. This is the XFEL in Korea. We designed the first RIXS experiment over there. So, you have to bring the spectrometer. They have the detector, but they have a robot arm. They don't have a fixed 2 theta arm. And, we managed to do absorption at different test samples, and we managed to see some inelastic intensity. So some very preliminary but encouraging data. What you're seeing here is RIXS spectra in hydrogen lithium iridium oxide on and off pump. So you pump very close to time 0, but before the pump arrives, you measure. And you measure the difference between those two pulses, and there is almost no difference between the pump. That sets your noise limit. That's what the red bar in here represents. And we're going to focus on that energy range, those 150 MeV energy range, where we expect to see any effects of the pump on the magnetic excitations. So you go, and I'm intentionally avoiding the minute panel for a second. You go further away, same pump, same conditions. This is very grazing pump and X-ray incidence. And you see no change within your noise rate. But then you go exactly at time 0. And there seems to be above noise for a decrease and increase of intensity, not only near the magnetic excitations, but also in the DD excitations, in the charge excitations. Now, this is very preliminary data. This is, something that these time-resolved X-ray experiments are extremely time-consuming. But we think that there are signatures that you can only see effects of the modification of the excitations, both magnetic and electronic, at time 0 when you have a circular pump. So this will be a signature of Floquet engineering. Now, probably not in the direction that we wanted to go, not in the direction where you are pushing the system towards Floquet. But we have ideas why this happened, probably not at the right pump regime. Probably, we need to think about doing some sample engineering towards decreasing decoherence. So this is something that we were excited and we are going to try to keep pushing. But let me say that this is suggestive of Floquet engineering at least. So, maybe in equilibrium, achieving Kitaev quantum speed liquid physics is hard, but Floquet engineering might emerge as a promising alternative. And there are many, many issues, right? You have penetration depth mismatch. These are hard X-ray, so they go through everything. Your penetration depth for mid-IR or IR pulses is 100 nanometers. How do you describe the effects of Kitaev-like excitations out of equilibrium? So I think there is a long run ahead, but there is a promising direction that one should also explore. So no, as Fasil said, we should try both things. Okay, and with this little bit of selfish advertising, this is, X-rays is only a part of my lab. We have a new ultrafast spectroscopy lab at Northeastern. This is our new beautiful building 5. The lab this was a few months ago. We are even closer to be fully functional. But if anyone is interested, please reach out, and I leave you with my conclusions in here. Thank you.
Okay, thank you. Questions?
This is technical, but so what does the -1 picosecond delay mean? Why is it that you need to do this? Yeah.
So what you're trying to do is, like all these pump probe experiments are actually coincidence experiments in a way, right? You want to measure when the 2 pulses reach at the same time. And what you're doing is you're changing the length of the paths that the pump and the probe have. So instead of measuring after the probe, you can measure before the probe. So you just make the probe pulse arrive earlier. And that gives you a signature for any heating effects, like long range changes, long time range that you've introduced in the material. So it gives you your baseline. Yeah.
Can you remind me what's the reason for choosing this pump wavelength?
Yes. So this pump wavelength, these calculations, when Martin did them, these were based on theoretical values. These are not the values that we have from the experiment. So what we are trying to do is, if I go back to the energy map, we are trying to avoid any absorptions, and we are trying to pump within the elastic line and the first DD excitations. So those energies, if Martin responded to me as often as he should, these calculations should have been done with not the theoretical parameters, but the parameters that we extracted in our paper. And so it corresponds to pumping in here, corresponds to pumping at the energy range where we expect the largest change to the Kitaev. But as I said, things are not easy. We pumped here. We should have pumped, the red line represents the pump energy. We should probably have pumped a little bit lower to fully avoid any absorptions and decoherence. It was a tough experiment. It was only 3 days, 72 hours. So I think at least that we managed to get something. And, at least I think it's very successful that we managed to get like 25 MeV resolution, which is for an FEL is actually really good. And that we actually managed to get some hard X-ray time resolved data.
Did you try slightly after time 0? Did you try slightly after time 0?
Yes. So 5 picoseconds after time 0, there is no change. So the only change above noise is exactly at time 0, which will be a signature of Floquet. Right? In Floquet, you only expect to see changes to your excitations or to your material while the pump is there, while the additional periodicity of the electric field is there. Anything after time 0 will mean that we have transfer energy to the system, and we have created a decoherence in this case. So the fact that prior to time 0 and after time 0, which sets our baseline, we don't see change above noise, it suggests that we actually are doing something when the pump is there. Go ahead.
Yeah, can.
Maybe I missed it, but so what Q are you at here? What momentum transfer? Do you know?
Very close to gamma.
Very close to gamma?
Yeah, 90-45.
And you have to do the grazing incidence to try to match the absorption
That's
length
right.
of the laser with the, okay.
Yeah, but we don't expect much momentum dependence anyway.
Yeah.
So I wonder if powders will be a good idea too. A pressed powder might be easier than a single crystal.
And then in this data, it looks like the largest change is actually kind of in the low energy tail of the inter T2G
Yes.
excitations.
So
do you know, can you assign that to something? Do you know what that is, or?
that's a good question. Martin and I haven't chatted about this yet. We don't know which orbital that could be. But that's right. Like the effect that we are seeing, the magnetic excitations, which will be this regime in here, it has also associated a change in the DD excitations. So that means that we are doing at least a partial absorption, or we are modifying the hopping, but not in the way that we want. So really, we should be trying to go somewhere in here. But
Yeah, because there are a lot of states still where you
That's
are
right.
pumping with your laser.
yes. But you know, that's also where maybe a little bit of materials engineering, maybe a little bit of nanofab to match penetration depths, that could help.
Other questions? So if there are no other questions, let's thank Alberto again. Okay, so with this, I'd like to thank all the speakers, all the participants, especially those of you at the audience that stick here at the end of the conference. So have a safe trip back home, and we really look forward to seeing you again in the near future. Yeah, thank you. Yeah, there is lunch. This is most important.